Hi, friends. All right. How about doing with text? I think I asked that. Did it close last week? Sunday or something? Let's see. Stop. Go lay down. Golly, sorry for your ears. Go lay down. Hold please. Sunday. It did close. Okay. Let's find out. What am I gonna do? Oh, great. Anybody like shocked or you're all pretty used to whatever's going on here now? Let's see. Oh, wow. Good grades. Nice. Yeah, 100%. Wow. Smart grades. Killing nowadays. Wow. Great job. Couple 98s. All right. Cool. Sweet. I looked at that, by the way. Get your 190. It's been one of those weeks for me. So, okay, cool. So here is the rest of the semester. Okay. We're gonna do chapter 26 now and Thursday. These are not like super advanced. I mean, they can get pretty crazy, but I'm trying to trim this down a little because the test is not that in depth with a lot of this. So for chapter 26, I would study it. Obviously, I'm not going to tell you like not to study it. But don't get like way too in the weeds with it, okay? So we're gonna touch on it. It's mostly gonna be chapter 25 and 20, whatever chapter it is. Okay, so that's this. This week we're gonna have some light lectures. I mean, they're like full lectures, but like I'm gonna kind of glaze over some stuff too. Next week we're gonna do reproductive, and then the week after that we're gonna have a test because it's Thanksgiving the next week. So in order to not give you a test on Thanksgiving, you're welcome, and then a test subsequently the week after. I'm going to be nice and let you study for your final with Thanksgiving. So tests the 17th to the 23rd, or whatever that is, 18th to the 24th, or whatever. And then we'll do a little bit of review sometime in there, probably that week that the test is open. I'm gonna think through that. And then I don't know if I can give you a test over Thanksgiving. I don't want to. I don't want to do that. Probably review on the 14th and then test the next week. I'm looking at my calendar. Okay, we'll see. Well, nobody does a test until Sundays anyway, so maybe we'll just do review on Tuesday and I'll open it up immediately after that. I don't know. I'll figure it out. Anyway, this week's chapter 26, next week is reproductive, and then we're done. And that's it. And that's all I have for you guys. So thank you for joining me on this journey. It's been fun. Tell your friends that this class is super fun and not stressful at all. All right. So anyway, I'm glad I got at least one laugh out of that. Okay. From the beginning. Oh, I need to share my thing real quick. So today is going to be fluid electrolyte stuff, and then we're going to go over urinary stuff in lab, and then just like we normally do, gross on Tuesday, histo on Thursday, and then next week we'll do repro stuff, gross on Tuesday, histo on Thursday. We'll call it a day. Okay. The final for the lecture is cumulative. The final for the lab is not cumulative. Okay. So whatever comes after the midterm is on the lab, but nothing before. Because that would suck to have cumulative. Okay. Anyway, so don't stress about the first half of the semester. And like, to be quite honest, cumulative is a loose term. It's probably I'm probably gonna recycle some questions. So just don't freak out. Okay, it'll be fine. Everything will be fine. All right, let me share my screen. We'll jump into it and we'll do this. All right, fluid electrolytes and acid-base balance. So today we're talking about fluids and electrolytes. Okay, so slideshow. Um, yeah, I guess it doesn't matter. Okay, this is Venus Williams for some reason. Okay, I guess we're talking about sweat. Right, so the water content in our body. So we talk about like pretty regularly that like you're mostly water, right? And that's pretty much true. Okay, so but it does vary. So like for example, an early embryo is 97% water. Think like the placenta is like a big sack of water, right? A newborn is more water, like big chunky cheeks, I guess. And then males and females are 50 to 60% water, and old people are 45%. Sorry, elderly people are 45% water. Okay, so the key takeaway from this is the older you get, the less percent of water you are. So, and there's reasons for that we'll kind of get into. Okay, but for the most part, from the beginning to the end, you're just losing water the whole time. You're just evaporating away. Okay. Sorry to get existential on you on election. So anyway, this is kind of the breakdown of that. Adipose tissue versus skeletal muscle largely determines differences between males. And this sounds kind of confusing, but basically what they're saying is males have a larger ratio of skeletal muscle versus adipose. I didn't say it. That was science. You can get mad at science. Please don't get mad at me. So the reason for that is because women burn more energy, basically. Or males burn more energy on skeletal muscle. Females use more energy with adipose. Okay, and there's a whole rabbit hole you can go down that. And there is a reason. I took a whole class on what the reason is, and you don't need to know the reasons. Okay, basically just know that the male body versus the female body are built for two different things, and one of them needs more adipose, one of them needs more skeletal muscle. Okay, so that's what the difference is. Okay, so more water in males versus females. Obviously, if you have more adipose tissue, you have less water, right? Because it's oil and water, kind of, I guess. All right, but where is that water, and like what organs are made up mostly of water versus not made up of water? Okay, let's break that down. So the brain is mostly water; it's 80 to 85% water, and by water, just water is a loose term here, okay? Let's go with liquid. I think it might be a better term. There is a lot of water, but there's stuff dissolved in that, okay? So don't think just like plain straight on tap water. Well, I guess there's electrolytes and stuff in tap water, so maybe. But not just straight up H2O. It's very complicated. Think more like you're mostly IV fluid, if that's makes more sense. So the brain takes up a lot of water. 80 to 85% of the brain is water weight. The teeth are only 8%, 8 to 10%, which makes sense. They're harder, right? And the brain is super mushy. Lungs are mushy, but a little less mushy than the brain, and the heart's pretty solid, so 75 to 80% there. The liver is 70 to 75%, it's a little less water, mostly because it's not like storing it, it's mostly like filtering it and pushing stuff out, okay? The kidneys are 80 to 85%, mostly water because you're filtering most of your water through there. The blood is 50%. I know what you're thinking, shocking. But blood is very viscous, right? There's other stuff in there. There's dissolved products, there's plasma, there's platelets, there's red blood cells, there's all kinds of stuff floating around in there. So blood, 50% water. Skin is 70 to 75%, and muscles are 70 to 75%. So that's just a little breakdown of that. Just kind of think for this, the mushier it gets, the more water there is, which Makes a lot more sense. All right. We have different compartments within our body. So there are intracellular, extracellular, interstitial, and plasma. So intracellular, so if you remember, I'm going to pull out a drawing pad because I had a brainwave 3 months into the semester. So if we remember a picture of a cell, right? And we've got a nucleus, and we've got little organelles kind of all over the place. All right, everything in white is water. Let's just put it that way. Okay, so a lot of this is water. I guess I could have just left it there, but anyway, everything in white is water, and everything that is solid or purple is not water. Okay, so there's a lot of water that makes up a cell, which is why we have those phospholipid membranes, right? Because you got to hold all that water. They're basically your cells are basically water balloons just attached to each other that do stuff. Okay. Then we also have interstitial fluid. So that's all of this stuff right here. Now, we also have junctions between cells. So if you have cells, like say, cuboidal cells like this, squamous cells, it makes sense that there's less interstitial fluid here, right? So let's call these not cuboidal, let's call them columnar. Okay, so let's put a brush border here, right? So here in the digestive system, you might have less water on the cell linings, right? In these squamous cells, because you have these tight junctions and water passes through, and all of your metabolites pass through those cells, right? So the point I'm trying to make is just because you have like this diagram that says like intracellular, interstitial, plasma, that can change based off where you are in the body. Okay, so you might have a lot of water that's intracellular in some places, like the brain. You might have a lot of water that is interstitial fluid in some places, like the digestive system, right? Because those are going to have like lumens, right? Like they're full of stuff, right? And then plasma also exists, but this is a low amount, right? So if there is a blood cell here, and a blood cell here, and a blood cell here, the plasma is everything between those, okay? And then the other thing down here that I want to kind of mention is all of your materials that travel between the cells and the plasma and capillaries are through the interstitial fluid. Okay, so you're not just, if you have iron in this plasma in the red blood cell right here, you're not just cleaning that off, right? What you're going to do is you're going to dissolve it into the plasma. It's going to diffuse into the interstitial fluid and make its way to whatever target cell it's going to get to. And there's not really like hemoglobin, for instance, that's carrying iron and oxygen. There's not really target cells. It's more like concentration gradients. Okay, so if the hemoglobin comes off here and it's got oxygen and it bumps into this cell, it's going to go, okay, well, this one's oxygenated, boing, this one's oxygenated, this one's oxygenated, oh, this one's not, and I'm going to get sucked in right here. Okay, so it's not like you're just reaching out and like poking those cells and delivering stuff. We're dealing with concentration gradients and fluid balance, and very complicated. I'm going to keep it easy though. Right. So for that reason, interstitial fluid makes up a large portion of total body fluid. Okay. Intracellular fluid, this is fluid that's within the cells. This is trapped. Okay. Obviously, this makes up the most. But interstitial fluid is not trapped. It is free floating. It is, in between spaces. It's filling cavities, right? So like if we have um, like a pericardium, right? And we have a fluid layer between that, that's interstitial fluid. It's filling that space, right? Same thing with like the digestive system and the abdomen, right? Cool. All right. So I said it's not water like H2O. There's a lot of stuff dissolved in it, okay? So electrolytes. This is your Powerade, okay? I am, just fun fact about me, I'm a Florida State alumni. We do not say Gatorade in this house. That's devil speak, okay? So, Powerade. And that's cations and anions. So, for those of you who have not taken chemistry, cations are positively charged. Okay. So cations, so Na plus, right? So you've got a positive charge right there. That's a cation and an anion, like chloride, for instance. Cl minus. Cool. So cations, anions. How do you remember that? Anarchy. No, I'm just kidding. It's not anarchy. It's a very stable environment. Okay. So anyway, um, great. So cations and anions. So these are your electrolytes. These are basically just elements with a charge, pretty much. Okay. We do chemistry with those. All right. And that's why they are here in the body fluid. We do a lot of chemistry with them. Okay. Non-electrolytes, so glucose, urea, proteins, lipid, and creatinine. That is 5 examples of like literally hundreds. So these are things that have a purpose. Okay. So we do chemistry with electrolytes. We do complicated chemistry with non-electrolytes. Okay, so this is very simple stuff. So this is like using those ions to like move electrons around. This is making bonds out of glucose, right? Or getting rid of nitrogen and urea, or building proteins to build cells, right? So very complicated things. Okay. And this is kind of a breakdown of all of those. Here's what I want you to get from this. All right. Electrolyte is listed here. Mechanism is listed here. I want you to get this from this. Okay. Highlight. Dang, just don't like it. Stupid. I'm gonna turn it off. Okay. Electrolytes. So think sodium and calcium, or sorry, not calcium, sodium and potassium. These are small. Okay. So if we look at a periodic table, something small. If we look over here, sodium, potassium, small. Okay. Very small. Calcium, a little bit bigger, but it's got 2 valence electrons. Okay, so it's a little bit bigger and it's got more activity going on with it. Okay, so all of this other stuff is big. Okay, so sodium and potassium, or sorry, sodium and potassium, channel mediated diffusion, co-transport, or active transport. Potassium, channel mediated diffusion, very passive, doesn't take a whole lot of effort to move it around. Okay. Other things that are bigger, right? Calcium, magnesium, iron, chlorine. These are big molecules and big electrolytes. A lot of carrier mediated transport or active transport. These take energy to move across the plasma membrane. Right? This is the concentration in all of those things. So sodium is mostly extracellular, and potassium is mostly intracellular. And we use that to maintain the concentration gradient. Okay, so how do you remember that? That's a cell, circle K, right? And then this guy comes up and he's like, "Hey, can I get in here?" He said, "No, no, you can't get in here. This is a circle K." All right, that was silly. You'll never forget it. That's the only way I've ever remembered which one's intracellular. Okay, so circle K inside, Na is outside. Okay, so we're gonna get into why and how we use that to our advantage at some point. Not quite yet. Okay, not yet. All right, so just remember that some of these are mostly found intracellular and some of them are extracellular. Okay, so Na and Cl these do a lot of stuff together. Salt, right? Like they're table salt. So NaCl are linked together a lot of times. They might do things together to cancel each other out. Potassium and phosphate, uh, phosphate, HbF4, always. Yeah, phosphate. These are tied together a lot of times. So these two go together, these two go together. And then magnesium does like its own thing, and it's not really magnesium and calcium are kind of interchangeable a little bit, and then bicarbonate does its own thing, and then proteins do what they want. Okay, they're all over the place, right? But the big ones to remember, NaCl is outside extracellular usually, and potassium and phosphate are intracellular. Okay. Okay. All right. Capillary exchange. So we've got positive pressure here and negative pressure here. So we've got plus 10 millimeters of mercury on. Sorry. Any questions on electrolytes? I shouldn't go that fast. Pretty straightforward. No. Yes. Okay. Ari hasn't told me I can move on yet, so I'm gonna wait. I don't even know what she's here. Okay, so that's electrolytes. All right, how does all this happen? Okay, it's dissolved, right? It's not like in these cells necessarily. So we've got positive pressure here and negative pressure here. Sorry, I'm reading down here, just making sure that I don't need to really touch on anything specific. All right. Mostly just remember this. There's positive pressure, so this fluid is being pushed out of the capillary. This has negative pressure, so it's being pulled into the capillary. Okay. You don't need to know like what the differential gradient is. Just know that it's higher over here and lower over here, right? Which makes sense, right? Because we have like capillary action, right? If you take a straw and you put it, like a really thin straw, and then you put it on water, it'll kind of suck it all the way up. That's kind of what's happening here. Um, so with resorption, and then if you blow out and put positive pressure on it, you're going to push it out of the straw, right? So that's kind of what's happening here. Right in the middle, nothing, nada. Okay. All right, facilitated diffusion. All right, glucose molecules are, glucose is a very, very straightforward example when it comes to facilitated diffusion, okay? The way that glucose gets into the cell is through facilitated diffusion, okay? So it's moving down a concentration gradient through through carrier protein. And for the purpose of this class, I'm not going to make you memorize the carrier proteins or how they work. Just know that in order for glucose to get into, actually, hang on, let's see this on the next one. Yeah, here we go. In order for glucose to get through a cell, through a membrane and into the cell, it's going to be mediated by sodium, okay? Or sorry, this is not complete. Oh, jeez. Okay. I'm going to show you a better picture, actually. Glucose. Okay. I like this picture. All right. This one is what I'm going for. Sorry, I don't like the slide pictures. For some reason, I feel like they just gave up on these last couple. slides because they're bad. They're not good. I don't like them. Why you just happened? Next one. All right, stop blocking ResearchGate, people. No matter how you vote today, vote for open access science. Good lord. All right. Do I have a picture that I can show? Jeez. Why do they all... This is annoying. I'm sorry. Should have been more ready for this. Okay. Here we go. Get bigger. Jeez. Oh, please. Oh my gosh. I literally don't care. Oh, shoot. Okay, this is big enough. Great. All right, so glucose gets into the cell. Okay, this is an enterocyte, but it happens like this, like a lot of places. Okay, so glucose will link up with sodium, and sodium is a symporter in this situation. Okay, and it will go through a carrier protein, a carrier transport, GLUT2 or GLUT3, whatever, a protein right here mechanism. Okay, so you need sodium, you need glucose. It's going to go in together, and then they're kind of like go their separate ways, right? Like this is equivalent to uh, like you need to be on the list of the club. And he's like, oh, yeah, I know that guy. And then you just kind of like go in together and then you go do your own thing. That's exactly what's happening here. Okay. So sodium and glucose go into the cell together. But because sodium is not supposed to be there, he's just using glucose as a, person to get him in the club. It's got to get out. Okay. So that's a way of sodium potassium pumps for. Okay. And we're going to get there in just a second. But just know that glucose and sodium go through facilitated diffusion to get glucose into the cell. And then from there, glucose can exit through carrier proteins. Okay. Now, since sodium is in the cell, and I'm going to draw a picture here because I figured this out, so I'm proud of myself. If this is the cell, say we have potassium in the cell. It's chilling, it likes it. And for simplicity's sake, let's say the charge is +1 in the cell, okay? Now, we've brought in glucose, which is neutral, but we've also brought in a sodium, okay? Now it's +2. Now the cell's charge is too high, so it wants to get that out. But in order to do that, it's got to kick out that sodium, and it can't just like bring it out like that. It's got to keep that same charge, okay? So the sodium is going to go out, and then potassium is going to come in. And this will make sense in just a second. And I know what you're thinking, but we still have the same charge, right? I get that. 1 second. Okay. So we're going to have a sodium potassium pump that will exchange those molecules, okay? So keep that in mind. So glucose is facilitated diffusion by linking together with sodium. It goes into the cell, right? And then it goes through these carrier proteins through the plasma membrane, and then into the cytoplasm, okay? And then from there, what does it do? Anybody want to guess? What does glucose do in the cell? I swear it's not a fair question. Sorry, I'll move this for what you guys are thinking. Any thoughts? All right. Well, since nobody says anything, I'll give it to you. It gets turned into G6P, and there's a Krebs cycle, right? Right. Okay. And gets burned for energy. Okay. So we've got that glucose in there. We've got the sodium in there. We've got extra sodium in there. Now we need to get rid of that sodium, right? Because sodium's not supposed to be. Yeah, exactly. Sodium is not supposed to be inside the cell. Why is it kind of looking out from outside the clip? We can't even get in, right? Okay. So sodium is inside the cell, and it's not supposed to be. So we need to kick it out. Okay. Now, how do we do that? We use something called sodium potassium pump. Sodium potassium pump. And this is an incomplete picture, and I don't like it, so I'm going to show you a different one. Okay. So, sodium potassium pump uses ATP to kick glucose out, or to kick sodium out, okay? This is a good picture. Let me see if it'll let me pull this picture out. I like this picture. I'll show it to you. Freaking research game, man. Here we go. Okay, that one actually worked. I like this one better. All right, so sodium potassium pump, okay? So we're gonna kick out, it's not just 1-to-1, okay? We're gonna use ATP and we're gonna kick out 3 of those sodiums, okay? Because it found its friends and it was floating around and we realized that this is a gang here, so we need to kick that gang out, okay? So we're kicking out 3 of them. Well, in order to kick 3 of them out, we're gonna use ATP and then we're gonna bring in 2 potassium, okay? So, for those of you keeping track at home, yes, we did bring it up, but because we're taking 3 minus 2 equals 1. Okay, so we're bringing it down, the charge down by 1 positive ion. So we started at 1 and then we added another, and now we're up to 2. We're going to kick it out in a 3-to-2 ratio, and we're going to bring that charge down back to 1. Okay. Did I overcomplicate that? I shouldn't have used 1 as an example. All right. We're going to have 1, and then we're going to bring in 3. So plus 3, plus 1, and then we're going to go minus 3, plus 2. We're going to keep that same charge. Okay. We're going to lose a charge basically in the process. Okay. So lose 3, add 2, bring that charge down. Why do we do 3 and 2? Because it's a slow process bringing the charge down. If you just kick out like all the sodium out of your cell, it'll bring it down, and don't bring any potassium in. It'll bring the charge down like way fast. Okay, and that will throw things out of balance. So we want to move charges slowly across the. Okay, that's why we do it that way. And in order to make sure that we're not doing it too quickly, we need ATP, right? So there's something that we need in order to get that process started, and that's ATP. Okay, so if we don't have ATP, and just know that this means that these steps take longer. Okay, so we're slowly adjusting the charge on different sides, and this is happening multiple times throughout the cell. Okay, like literally thousands of times across the plasma membrane. We're maintaining a neutral charge on the membrane. It's not neutral. We're maintaining the same charge on the membrane by doing this process over and over and over again and eliminating it with ATP. Okay, it's a buffer system. Think of it that way. So we also use phosphate in that because you have to ADP, but I digress. Okay, water balance. All right, any questions on sodium, potassium, Tom? There's a lot of like named enzymes, proteins, and stuff that go into this, and we don't need to get into that. Just for the purposes of this, know that you need 3 sodium and 2 potassium for the pump to work. Okay, and ATP. Right? Cool. Let's talk about easier stuff. Water balance. All right, so we're constantly secreting and then reabsorbing water throughout digestion. Okay, we kind of talked about this a little bit, but think if you drink and eat, right, you're going to bring in 2,000 milliliters of water. You're also going to secrete, say, 1,500 milliliters of water. Okay, so a lot of water is starting up at the very top of the process. You're going to end up with a lot after gastric secretions and other secretions. So we're bringing this all the way up to like 9,000 milliliters, which is a lot. Then we need to resorb a lot of that because we've secreted a bunch, but we've also taken in new water. I was going to say took in. I was like, that's wrong. We've also taken in new water, right? So we need to resorb that, and then we need to get rid of a certain amount that's appropriate and not going to lead to dehydration. Okay, so we're going to lose a little bit. We're going to resorb some in the colon, and then we're also going to resorb most of it in the intestine. Okay, water is good. It keeps your body temperature stable, which is awesome. Okay. So if you have too little water, say you've been evaporating it off your skin because you've been exercising, say you have explosive diarrhea and have been pooping it out. There's lots of different reasons you might be dehydrated. Okay. Here's what's going to happen. You're going to be thirsty, obviously. All right. So starting off with a low H2O in the body, okay, that's going to decrease our blood volume and increase blood osmolality, okay? The reason we're increasing osmolality is because we've got more concentrated blood, okay? So we have less blood and it's more concentrated, okay? So let's start with decrease in blood pressure first. In blood volume first. That's going to decrease the blood pressure overall, and then that will cause our blood to release angiotensin 2. Our lungs, great answer. And the reason for that is because of the renin-angiotensin aldosterone mechanism. Okay, so through decreased blood pressure, we're going to go through that renin cycle and then lead to angiotensin 2, and then that will stimulate thirst in the hypothalamus. Okay. The other thing that's going to happen at the same time is we're going to increase the concentration of our blood. Okay, so increase blood osmolality. We have osmoreceptors in the hypothalamus that will cause you to have a dry mouth, and then we will stimulate thirst centers in the hypothalamus. This is like the physiological response. This is more the physical response. Okay. So we'll get thirsty, we'll drink water, we'll decrease blood osmolality, and then we will process and filter that water. We'll pee it out, we'll poop it out. We got a lot of different ways to get rid of water, and then this whole thing will happen all over again. Okay. ADH, antidiuretic hormone. So we drank some water. We need to tell our body to keep the water that it's got, right? Because we don't want to get dehydrated. So we have something called antidiuretic hormone. So diuresing is like filtering out, right? So antidiuretic, right? We're not filtering it out. Okay, so that's produced in the hypothalamus, which is the osmoreceptors, right, are there. So we're going to release something by the hypothalamus and release it to the posterior pituitary. right? So remember that all the way back in the first chapters. It will cause the kidneys to retain water, so kind of bringing it all the way back around, right? We're going to act on the kidneys, and we're going to retain the water, and we will constrict the arterioles in the peripheral circulation right here, and it won't release the water. Okay. I don't know why it's harping on behavioral social behaviors in mammals. I mean, everything affects social behaviors in mammals. So, I mean, all right. One other thing. Any questions about the hormones involved in this? ACE inhibitors, ADH. Yeah, cool, awesome. All right, aquaporins. Think of aquaporins as proteins that create vesicles. Okay, so if we've got, I like this image kind of, but let's kind of look at it from a different angle. All right, so if we've got, say we've got a protein here, 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 protein here, protein here. Okay, so if water comes in, we go that way, and then we start building up that water balloon, okay? And eventually these will kind of pinch off. So you'll get like this. That's your storage vesicle, okay? These proteins are called aquaporins. And aquaporins are basically just moving their pores, right? They're protein-lined pores that are moving water through the cells and into the bloodstream, okay? These exist a lot in the digestive system, so in the urinary system. Okay, so we've got water that goes into these aquaporins and push it through, and then they eventually get to the other side, and they just kind of release their vesicles. Okay, so it goes into the bloodstream. Okay. These are in the collecting tubules, right? So like these are the ascending tubules and kidneys. And this basically means you're taking something that's like passive diffusion, which is what water does, and you're like speeding up that process. Okay, so you've got like a pool, and you're just chucking water balloons across the side of the pool. Okay, all right. Things that can disturb the water balance. Dehydration, right? So that's not good because you don't have enough fluid in your body. Diabetes insipidus. Why would diabetes mess with water balance? Specifically electrolyte balance. Constantly being out sugar. Slightly, but not the answer I'm looking for. It's earlier in the process. I'll give you a hint. It's got to do with electrolytes. I'm not calling again if nobody answers. Off screen. Glucose. Because you need sodium to get glucose in the cells, right? So if your glucose is too high in the blood, right? You probably don't have enough sodium getting it in there, right? So you're throwing off your electrolyte levels because either the sodium is getting trapped in here, or you just straight up don't have enough electrolytes to get that glucose in, which is why it's still in the bloodstream, which is why if you prick your finger and you test your glucose levels and you have diabetes and your glucose levels are high, you can assume that it's floating out here and it's not intracellular like it's supposed to be. Okay. So diabetes, and if your sodium's off, your potassium's off. If your potassium's off, your sodium's off, then probably like other electrolytes are off too, like calcium or other stuff. Right. Hypotonic hydration. So hydration where you're drinking too much water and you're not drinking electrolytes, right? Like this is why we have Powerade and other electrolyte drinks, because you got to replenish those electrolytes as well. Uh, you can't just water down your electrolytes. You've got to have electrolytes, okay? Otherwise, you won't have sodium, and then you can't make glucose. Cool. Electrolyte balance. This is what's this one? Okay, this one is. All right. All right, how do we regulate all these? So sodium is affected by aldosterone and ANP, right? So ANP is alpha natriuretic peptide, I think. Hang on, let me Google it. ANP, atrial, I should have. It's in the atrium. Okay. So it can also be influenced by estrogen, which will enhance sodium resorption, progesterone, which will decrease resorption, and glucocorticoids, which will enhance sodium resorption. Glucocorticoids, glucose, sodium, as buddies, right? So it will enhance the resorption. Okay, these two are connected. All right, by aldosterone. Okay, so we've got blood potassium levels rise. That triggers an aldosterone release from the adrenal cortex. And if potassium levels are rising, then sodium levels are falling. Why? Because there's more potassium in the bloodstream, which is not where it likes to be. It likes to be intracellular. And if there's more potassium in the bloodstream, that means there's more sodium in the cell, which is not where it's supposed to be. So aldosterone will be released from the adrenal cortex. It'll target the kidneys, which will release potassium. They'll tell the kidneys to stop resorbing potassium and releasing it, and then sodium will be reabsorbed by the kidneys instead, and then blood sodium potassium levels will normalize. Right. So we're just kind of like balancing it out, right? We're kind of setting the level. Cool. Rated angiotensin. So we kind of killed this horse already. So just remember that aldosterone is a product of this rated angiotensin mechanism, and it will stimulate sodium and water reabsorption in the nephrons. Okay, so in the convoluted tubules. Okay. All right, so regulation of potassium, it moves the opposite of sodium, right? And it's also regulated by aldosterone and ATP through all those processes that we just talked about. Chloride, so chloride regulation is similar to sodium. Remember, sodium and chloride go together, right? Like they're positive and negative anions, or ion. One's a cation, one's an anion. They're positive and negative ions. They attract each other. Okay, so if aldosterone is influencing sodium, increasing sodium, it'll increase the blood chloride levels. Okay. If ANP is decreasing the sodium, it's decreasing the chloride levels. Okay. Calcium. PTH raises blood calcium. Anybody want to guess what PTH stands for? You've been tested on it. Parathyroid. Oh, great job. Awesome job. See, look, you're going to be doing great with that cumulative final. All right, so PTH is released into the bloodstream, and it increases osteoclast activity. So we're going to break down more bones, and we will increase absorption in the intestines. So we'll take in more calcium in the intestines, and then we will also reabsorb it in the kidneys. We're not getting rid of calcium; we're keeping it. Okay. Calcitonin does the opposite. All right. So this is just an example of that. So this is pictures. So the chief cells in the parathyroid glands release the parathyroid hormone PTH. Okay, that floats all the way to the bones, right? So it goes into the bones, inhibits osteoblasts, and stimulates osteoclasts, so they're breaking it down. And then that will trigger the kidneys to reabsorb the calcium. Then we'll also reabsorb we'll convert calcitriol in the kidneys, and that will go out in the bloodstream, and that will tell the enterocytes to bring in more calcium, right? And then from there, they'll increase. Calcitonin will be released, which will basically tell the body to slow down on that, chill out, we're breaking down our bones, and then we go in the opposite direction, okay? Cool. Phosphate is regulated opposite of calcium movements because they go together. So influence of parathyroid hormone has the opposite effect. Okay. All right, that's all I got. This is acid-base balance, and we're going to go into it later. And fair warning, I hate this, so I'm going to remove some of the test questions if they're on. I don't like acid-base balance at all. It's important, but it's kind of confusing to me. So, all right. Any questions about anything so far? No. Okay. All right. Well, if there's no questions, I'm gonna go eat dinner, and I'll see you guys in lab. We're learn about the urinary system. Okay. Okay. See you later.